Okay, so here we are, and goodness. Entropy, we've talked about it before. We'll talk about it again just to recap. Entropy means disorder, chaos. And here we have a recap on table I. So reference table I, you should have that out. We'll talk about how entropy will increase or decrease in certain reactions. So phases of matter, we'll talk about solids, liquids, and gases, but we'll also talk about aqueous. Although it's not a phase of matter, it's a situation, a solution. So which would have the least entropy, would have the least disorder, would be the solid, then a liquid, then aqueous, then gas. So again, and of course this is going to be in the way, but there's a solid, particles close together, tightly packed. Liquid, a little bit more smushed, not more smushed, a little bit further apart. Aqueous, now check it out. We have, and that green's a little obnoxious. Notice we've got the green, which is probably the CLs, and we've got the little yellows, which are probably the NAs, by the way, charged. And then see all those little Mickey Mouses? That's water. So notice how this is more disordered than this, because at least all of this is just purple circles. There's all kinds of differences going on here. And then gas, we've got particles moving all over the place. Crazy. So more entropy even further. Now, rate of reaction. Rate means speed or time. This is how fast a reaction occurs. And we talked about, how could we get something to go into solution the fastest, rate of solution, but rate of reaction, you've talked about that. Collision theory. Atoms react to form products when they collide as long as they have enough kinetic energy. If you have effective collisions, I'm sorry you couldn't see that. Particles lacking enough kinetic energy to react will bounce apart unchanged when they collide. Something else I wanted to mention is you need to have enough oh, that's not a good color. Come on. Pen color. Let's just do black, I guess. You need proper orientation and sufficient energy. Oh my gosh. I'll mention it again. I have one of those optical mice pens, and it is dreadful. So my regular old mouse works better. So remember we talked about an effective collision is kind of like me wanting to punch a window. So if I punch the wall instead, the wall next to the window, I didn't have the proper orientation. If my fist moves so slowly that it just barely touches the window, that's not enough energy. So if I really wanted to break the window, I need to orient my fist with the window, and I need to give it enough energy to go through. Of course, I don't recommend doing that. Things that are going to affect the rate of reaction. A lot of this should be review. Maybe not this one, though. Nature of the reactant. Some things just go faster than others. If you have more bonds in the compound, it's going to require more energy to break. Now, remember bonding. We've got sharing of electrons, and we've got transferring of electrons. So in ionic, which is the transfer of electrons, they have fewer bonds and will react faster. Ionics, well. Things that are molecular, which are covalent, this is where you share electrons. They have more bonds and react slower because you've got those orbital overlaps, and that's harder to break. So some things are just going to react faster than others in general. Temperature. Higher the temperature, you're going to have more particle movement, more particle collisions, and a faster rate. So they're going to react faster, higher temperature. Concentration. That would mean things like molarity. Okay? So if you have a higher concentration, there's more particles in there, which means those more particles are going to be more likely to collide and increase the rate. Pressure. Now, you should know that pressure only is for gases. Sorry, this is in the way. If you increase the pressure on a gas, there will be less room for particles because you'd be pushing them closer together, which would be more collisions, increase rate. So a lot of these are increase. So increased temperature, increased concentration, remember brackets, the molarity. Increased pressure, but again, only of gases, all going to increase the rate of the reaction. Surface area. So if you wanted to react something, so let's say I have zinc, and I'm going to react it with HCl, hydrochloric acid. And you know it should react because we've seen it. Should I have zinc that are in little chunks, or should I have powdered zinc? The powdered zinc is going to react quicker with the HCl and have a faster rate. So the powdered zinc has a higher surface area. So again, this is a direct relationship. Increase the surface area, you're going to increase the rate. Because again, there's going to be more interaction between the particles. All of these seem to be increased so far. Now, a catalyst, maybe you are familiar with that term from biology class when you talked about enzymes. Enzymes are a type of catalyst. You can have non-biological catalysts. Enzymes are biological catalysts, but a catalyst is a substance used to decrease the activation energy of reactants by providing an alternate reaction pathway. Okay? It also does not participate in the reaction at all. So I'm going to add that. If you want to add that. Does not participate in the reaction. Meaning, if you add a catalyst, you're not going to get a different end result. The catalyst is used up. It speeds up the rate of the reaction. It does not change the reactants or the products by using a catalyst. It's a shortcut. It gets you there faster. So here we have a potential energy diagram. And this is normal. With a catalyst, though, notice that instead of going all the way to the top here, we'll just go here, and that will get you there faster. So notice that we did not change everything. We only changed the amount of activation energy, because activation energy here, now look, activation energy with the catalyst. It's less, okay? What else did the catalyst change? Did it change this? Whatever A is? No. Did it change C? No. Did it change D? No. It would change the activated complex, which is not even included. That's the bottom to the top, because now it would be bottom to the top of that. It won't affect all those other things. It won't affect your difference. It won't affect P of reactants and the products. So again, a catalyst, if you increase, the catalyst will increase the rate of reaction. Now this is the opposite. You should maybe know from your context clues that an inhibitor is going to stop things, slow it down. If I'm going to inhibit your ability to drive away, I'm going to take the keys to the car. I'm going to hide the keys. I'm going to make sure that you don't have any money for gas. I'm going to pop the tires. Those are all inhibitors, okay? So an inhibitor is a substance that will increase activation energy to slow the rate of a reaction, making a reaction happen slower. Why would we ever want a reaction to happen slow? Well, there are many reasons why. If you want to be able to measure it, if it's too fast, you won't be able to see everything that happens. Or what if the reaction isn't something you want? What if you want to stop a reaction of, say, I don't know, bacteria growth? So you use food preservatives. Those are inhibitors because they prevent the growth of bacteria in your food. And so that will actually decrease the rate. That's the only one that is an inverse. And that is it for today. All right, if you've got any questions, please let me know. Thanks.